As Doug mentioned, Brian Kimball, Katie Walton Day, and myself have done a series of water quality studies down here. And these are what we call synoptic studies, where we basically take a stream reach and map water quality spatially. And so we've done a lot of these studies, and one of the first things that we do is actually do the reconnaissance, where we walk the stream and we decide where we're going to sample. And you know, we don't like drive around in a truck and pull up to a road crossing and kind of walk around a little bit, and we don't walk on the stream bank. We literally start at the top and start walking downstream. And one of the reasons we do this is back when we first started, we really didn't have GPS. And so we take a 50-meter tape and walk and measure all the sites and all that. But the other thing is you see little seeps coming in, and you see things that the locals might not even know about. So anyway, today I'm going to talk about Upper Cement Creek, a reach I've walked a couple times at least. And hopefully you can see the pictures and plots here, but if not, I'll try to describe them as best I can. Let's see. How do I do this? A few acknowledgments. A lot of my funding comes from the Toxic Substance Hydrology Program. I've been real fortunate to have funding from them for a number of years. For example, they funded part of the Abandoned Mines Lands Initiative we did back way in the late 90s. Also, a few years ago, Brent Lewis from BLM came to me, and we had been working together, and he said, well, BLM would kind of like to know what background conditions are in Cement Creek. And we already had a calibrated model from Cement Creek and some data, and so it was a really good idea. And but the first thing I thought is, I said, well, this is a really complicated problem. There's really no established method for pre-mining conditions, so we're just going to break off a little chunk of the stream. We're going to work on the Upper Gladstone area first, and that should be pretty tractable, and we'll work on the rest later. So that was the first phase, and that was a couple years ago. And as you might know, I haven't given a presentation on that yet. But what I started doing is just looking at our historical data from that area, and I got a bit sidetracked. And so apologies to Chris Dobler and BLM, but that's the way science is. And anyway, I started working on some of the historical data from up there, and I showed it to Ian, and he had some interest, and so he pitched in a little bit. So this is really a collaborative effort between those three entities. And then, speaking of cobbling things together, I pulled data from a lot of places, and a lot of people helped me out, and their names are there, and if your name's not there, it's because I ran out of space. But anyway, data comes from a lot of places. Just an overview of what I'll be talking about the rest of my time here. I'll go over what I'm talking about when I refer to Upper Cement Creek and the problems up there. One of the things that some of you know about is the changes in adit flow rates that have happened over the past 20, 25 years. And then we'll get into this concept. One of our colleagues made this great quote, that the truth is in the stream. And that's really this idea that the watershed really integrates what's going on up above it. You have obvious inflows like mine tunnels, but you also have groundwater coming in. So if you sample in the stream, you can really get to what's going on. And then finally, I'll look at these changes over time in Upper Cement Creek in the context of the bulkheads that have gone in. Oh, did we skip one there? Yeah, so some of the data sources. Back in the 90s, Jim Herron and Bruce Dover and others did a lot of reconnaissance up here and did a lot of sampling. So some of their data is in the database I've compiled now. Obviously, EPA monitoring. There's a little gap in the data, actually. But back when Steve Way started the Red and Bonita project, the monitoring kind of kicked back in. So we have EPA data, USGS studies that I've been involved in. Peter sent me the ARSG database, which has been useful. And then finally, I didn't really know about this much, but there's a wealth of data in Sunnyside's annual reports that get filed to the state. Go ahead. All right, so why study Upper Cement Creek? First of all, just a little look at things. This is Upper Cement Creek. You drive up the Cement Creek Road, and here's Gladstone. The South Fork comes in here. At the upstream end, Ross Basin would be up in this area. And as you come downstream, there's the Mogul, the Red and Bonita, the Gold King flows into the North Fork and down, and then the American Tunnel is right at Gladstone. So why are we interested in this place? Well, there's 4 draining adits up there, and since the Longfellow Kohler, or the Kohler Tunnel has been plugged, those adits now account for about 40% of the zinc load in the basin. We already know there's documented changes in these adit flow rates that are of interest. And the key thing about the data from up there, it's really unaffected by the treatment that's gone on at Gladstone over the years. If you're going to look at data from the Cement Creek gauge, for example, it's really hard to tease out changes over time because sometimes the treatment was on, sometimes the treatment was treating all of Upper Cement Creek, sometimes it was off, etc. So if we can just concentrate on this area, we can learn a lot about what's happened up there. Here's one of Kirsten Brown's great things of the mine workings. The reach we just looked at was here coming down from the Mogul. But in the subsurface, we have all these mine tunnels. So initially, the Sunnyside mine, shown here, was mined, and they actually hauled the ore and stuff down Eureka Gulch and down the Animas side. And then, years later, they drove the American Tunnel into the Sunnyside mine to haul the ore out the Cement Creek way, and also drain the water from the Sunnyside. So as you can see, the American Tunnel is quite long. There's workings from the Gold King, Red and Bonita, Sunnyside, and then also over to the Mogul. So why bulkhead? Well, first of all, if you've never seen a bulkhead, you're not missing much. There's Jeff Graves at the Penn Mine near Keystone. And so why would you put a concrete plug in one of these mines? Well, the first idea is to reestablish the pre-mining groundwater table. A lot of these tunnels were designed to drain the mines, so by plugging it, you reach the groundwater up to where it used to be. Hopefully when you do that, you're reflooding the mine workings and preventing oxygen from getting in there and slowing the rate of oxidation and the generation of metals. That's another reason. And then it also can prevent blowouts. So at the Penn mine, for example, before the bulkheads years ago, they had a big flush, a big snowpack, and there was actually a flush from there that killed fish down in Keystone. So why not put in a bulkhead? Well, you could make things worse. Andre just talked about the freshet, and it's the same idea. You have these mine workings that have been dry for a really long time, and then all of a sudden you're flooding them and dissolving all these metals and producing acidity. So at least for the short term, you can make things worse. If you have extensive mine workings, you can make things worse for a long time. Another problem is you don't know where the water is going to go. Before the bulkhead, you know where it's coming right out that tunnel. Once you put that plug in, who knows where it's going. Here's Upper Cement Creek again. I just want to kind of simplify things. We have the Mogul on the far left there, upstream end, then the Red and Bonita, then the Gold King. The American Tunnel is kind of right in the middle of my diagram here. The South Fork comes in, and there's some mines on the South Fork side, the Natalie Occidental, also known as the Silver Ledge, and the Black Hawk, lead carbonate mine is also over there. Those two branches come together and head downstream. But as you know, there was a treatment plant in Gladstone back in the 90s. There's a treatment plant there again now. So downstream of this confluence is all treated water. And as I was saying, it's kind of nice to study this upstream portion because it's unaffected by treatment. All right, so here's the adit flow rates over time. So on the left there is the flow rate in GPM. Along the bottom is time. Actually, if you look at the top, it's probably better. It starts in 1993. It goes to about 2010 or something like that. And these vertical lines represent different points in time. The one on the far left was a joke I was going to tell, but you'll have to ask me about it over cocktails. The other lines represent when the bulkheads went in the American Tunnel. So American Tunnel bulkhead number 1 went in 96, And then number 2 and number 3 went in the 2000s along with the mogul bulkhead. So the big things that happened, the big changes, is that after American Tunnel bulkhead number 1, the mogul flow rate started to increase. And then after 2 and 3, the Gold King and Red and Bonita also started to increase. Good. So anyway, like I was saying, I kind of dove into our old data and to take a look at it. And these are a couple plots that are where the x-axis is with respect to distance. So this is at 99. We did a study. And here's the pH in this reach above Gladstone. So this is above the mogul, pH around 6. The mogul discharge comes down, drops it down to below 4. It stays below 4, past the Red and Bonita. North Fork comes in, drops a little bit more. So that was our study from 99, just the pH part of it. I've shown that same thing again here. And the line here represents the stream data. And then the dots are the inflows that we sampled. So I've added to this plot not only the inflows from 99, but also from 2012 when we did some work with EPA. And in the case of the mogul, the 99 and 2012 pH is about the same. Same thing with the North Fork. But a weird thing happened. In the Red and Bonita, the pH went from below 4 to up above 6 in that time period, from 99 to 2012. Well, what really happened, not only did that pH go up, but if you look at the stream data from 2012, it also went up at the Red and Bonita and also way upstream here. So what the heck's going on? So, you know, I scratched my head a lot, and next thing I know, I was in spreadsheet hell. I started compiling all this data and ended up in this time series database, and it's really been a long process, and I'm just getting to the fun part where you start to plot things. And what I'm showing you today is just kind of scratching the surface of that data set I put together. So I have this time series database, and so one option is just to plot the time series of the adits. How has their flow changed? How's the chemistry changed over time? And we could do that. But, you know, like I said, not only did Red and Bonita go up, but also the stream went up. And you know, there must be some other things going on here. So if we just look at the adits, we've kind of missed the picture. So when I was here in October last year, I walked the stretch for old time's sakes, and I found out where this inflow was coming in, where the pH was actually increasing. And you damn near trip over it, because the stream goes from being orange from iron precipitation, and this inflow comes in and it turns white. So I'm pretty sure we didn't miss this in 99 when we walked this reach. And I think this is a new inflow that brings in a lot of water. And I haven't done the exact, we should really get a good GPS, but it's about the same elevation as the Red and Bonita mine. So I'm calling this the smoking inflow. So like I said, we want to look at the stream, and we had this colleague, Diane McKnight, and I think this is attributable to her. You know, it's been so long, we don't really know where things come from, but I'm going to give her credit for this. And the idea is that we want to look at the stream, and that really integrates what's happening upstream. So I started looking at reports, and I had a few of them that had been emailed to me, but then Alan Sorensen said, well, they file annual reports every year. Well, it turns out right above the American Tunnel, Sunnyside has sampled every month since 1987. And as far as I know, no one's ever plotted this data. It's all in these PDF reports. You have to like cut and paste out of the PDFs to get the data out. And so what I'm going to show you in the next few slides is the data from these reports. So the idea, the truth is in the stream. We're going to look at stream load. You multiply concentration times flow, and you get the load, the mass per time. If you're standing on a bridge, how many kilograms go by you in a day? All right, so these are the American Tunnel loads. I'm gonna get to that site on the stream above the American Tunnel in just a second, but this is kind of the obvious part. If you plug the tunnel, the loads are going to decrease, right? So these are a little bit of apples and oranges. The initial data they had was total zinc. This is dissolved zinc, but zinc's fairly conservative, so they're probably pretty comparable. So we have some early data here showing the load from the American tunnel itself. And then we have a gap. I think I was missing some flow data here, so you couldn't do the calculations. And then there's data right after that first bulkhead goes in. And so you could argue this data is a little bit lower, but I assume the flows increased a little bit over time, a little leakage on the bulkhead. And so there's maybe a little decrease. But then when that second American tunnel bulkhead went in, you really dropped the load coming out of the American tunnel. So, you know, in that respect, the bulkheads have done some good. So here's that site above the American tunnel over that same time period. And there's a little bit of noise in the data. But if you kind of look at these clusters of points, these are samples from every month, so I haven't really looked at what's causing these. But here's this kind of cluster of points before the first bulkhead went in. And then that first bulkhead goes in, and you see a little increase coming here. And then we're missing some flow data again, and then also another increase after the second and third ones went in. So it looks like some of that water that's being blocked from the American tunnel is coming out upstream. So what's the net effect of these two things? We've reduced the load coming out of the tunnel. We've increased the load coming in upstream. Next slide. So this slide shows those two loads added together over that same time period. And so the net effect is a positive one. The loads have generally decreased. It's not as dramatic as the decrease in the American tunnel, but we've decreased the load by putting those bulkheads in. And one possibility is that we've actually decreased the rate of oxidation and release of metals. Before we pop the champagne cork, we got to think about the South Fork of Cement Creek. So it's been documented in that plot I showed earlier, the Blackhawk mine, which is on that side of the watershed, the flow is increased in that mine too. So it's possible that I haven't accounted for the load coming from South Fork. So here again, in blue is our site above the American tunnel, that increase we just talked about. And then here's the South Fork mouth load. And over time, it's been pretty steady. So it looks like we can possibly pop the cork on that thing. But there's a couple questions. Are there other outlets? Are we shipping water over to Devon and Red Mountain Creek? Is the system in equilibrium? Is it possible that there's maybe some bad news still on the way? But in general, it does look like there has been a good effect of the bulkheads. So to conclude, the American tunnel load has decreased due to the bulkheads. Some of that decrease is offset by this additional load coming down Upper Cement Creek. And the net effect is a decrease in load leaving Gladstone. And that's probably attributable to less oxidation. But there's also this possibility that it's going somewhere else. The next steps in this are to look at other metals. Today we just looked at zinc. I'm going to look at cadmium and copper probably next. And there's other questions we can answer with this data set. You know, what's really going on with the Red and Bonita? You know, one possibility is that higher pH water from the American tunnel is causing that increase in pH. But we really want to investigate that. Another really curious thing about Upper Cement Creek is that the Gold King has 7 milligrams per liter of copper. And none of these other adits seem to have anything close to that. But I did notice that there's some seepage out of the Mogul wetland that has high copper concentration. So is there any linkage between those, or is that just a coincidence? That's it. If anyone has any streams they want walked, please get a hold of me. And looking forward to talking to you afterwards.